Hello. In this video we will show activity 3 for Lab 8. So now the objective will be to analyze experimentally the magnetic force exerted between two currents. As a reminder, there are two sources for the magnetic field. One is the permanent magnets. Permanent magnets, we know they create field lines from north to south. And the second source of the magnetic field are the currents, and that's the thing we will study in this activity. A current flowing on a conductor like this will create a magnetic field around, following the right-hand rule. So imagine we have two currents, I1 and I2. One is the source of the magnetic field, and the other is the one which is feeling that interaction, that source. Okay. So in this case, I2 will be the current creating the field. What is the force exerted on I1 by B2, which is the field created by I2? Well, this is the force created on the current I1 using the field produced by I2. So it's the same formula as before, but now taking into account that the field is not created by a permanent magnet. Now the field is created by a current. Similarly, there will be another force exerted on I2 by the field created by I1. So how do we do this in practice? Well, again, we will use a DC voltage source to create the current, and this current will be feeding two coils. We will check the currents using a digital multimeter, and we will have two coils, one for I1 and the other for I2. Actually, in the experimental setup we will propose, we will have the same current flowing on both. So I1 equals I2 equals I. We will use again a digital balance as in the previous video, because the force will be indirectly measured by measuring the weight, the attraction or repulsion between the two wires. This is the experimental setup. As you can see, we have a voltage source which is producing a current, and this current is introduced in one first coil. The same current will be feeding the secondary coil. So both coils will have the same current. And depending on the direction of this current, if the currents are the same, there will be an attraction. If the currents are opposite, there will be a repulsion. Let's see this in practice. This is the force exerted by one onto the other. Okay. Here, because I1 and I2 are the same, we just substitute by I. Okay. And N is the same number of turns on both coils. That's why we have N squared. L is the same length on both, and D is the distance between them. So how can we simulate this? Again, we will use the same simulator. You have the slides, and once again you can click on them to get to the simulator. Let's do a practical example using this simulator. So once again, when you enter to this simulator, probably you will be having something like this. First thing you want to do is to clear all, and we will start adding things. First thing we will add is a current. go here, add current, for instance, the positive one. Okay. We click on the screen and drag and drop. Oops. This is not very nice. I will repeat this. Drag and drop, something like this. Okay. Now, if you visualize the magnetic field will give us an idea about the direction of the current. Magnetic field, as you can see, is counterclockwise. Following the right-hand rule, counterclockwise means that the current is directed to us. So it's perpendicular to the screen and directed to us, right? We can see here the current. This yellow means current is pointing to us. Let's add a second current, now negative, for instance. Okay, another piece of cable like this having negative current. Negative current is drawn in another different color, and this should have the opposite direction. How do we check the direction? Again, we can go here to the magnetic field view, and as you can see, if we concentrate our attention in this section here, the direction of the field lines are clockwise. Clockwise means that, following the right hand rule, the direction of the current is entering into the screen. So perpendicular, going inside. If we see the visualization of the force exerted between the two, this is what happens. The force exerted on two cables having opposite directions for the currents is a repelling force. Is the opposite than for charges. Remember that charges, the electric field for charges and the electric force, Coulomb's law for charges, it's attractive if both charges have different signs. For magnetic field is the opposite for currents. Two currents flowing in opposite directions will repel each other. Let's see what happens when we have two currents on the same direction. So we click on clear all, and we add, for instance, two positive currents. Same will happen with negative. Okay. So this is the current, yellow, and we will add another yellow. Okay, just click here, and these both have the same direction. How do we check this? Again, we go to the magnetic field view, and as you can see, for the upper wire here we have counterclockwise direction, and the same here. Here we have counterclockwise direction. Both have the same direction, counterclockwise. Counterclockwise means, using the right hand rule, that the direction for the current is directed to us on both. What is the force in this case? If we go here to force, show force, the force is attractive. So two currents having the same direction, they produce an attraction between them. We can check the same if we do with negative currents. Just add a negative, will be probably blue. That's the color used for this simulator for the negative current. We add a second negative current. Sorry, I will do it again. Negative here, negative here. We want to see again the magnetic field. The magnetic field is clockwise. For positive is counterclockwise, for negative is clockwise on both, as you can see. Clockwise here, clockwise here. Clockwise means the current is entering, that's the negative direction. Okay, positive is directed to us for the current, negative is entering into the screen. What is the force? If we go to show force here, force again is attractive. So two currents, no matter if they are positive or negative, but the same sign, same direction, will produce an attraction between the wires. Two currents with different signs, positive, negative, or negative, positive, will repel each other, will do a repulsion force. Okay? So now your goal is to do activity 3. We will measure the magnetic force between two current-carrying conductors. Things you have to do is, first, you have to determine theoretically the direction of the magnetic force produced by the following setup. Okay, the setup on figure 6. And you want to also simulate this setup, right? You want to go to Fast Simulator and draw the currents and check if they will produce an attraction and a repulsion based on the analysis of your setup, right? Again, do not forget to take screenshots of the simulator, Alt print screen, and paste those screenshots on your lab report. And finally, you want to do also some numerical analysis. In this case, I'm providing to you the measure of the current already square. The current square measure here for different values from 0 to 1, and I'm providing to you the corresponding measurement of the mass, which is measured by this digital balance. Okay? Again, you have to think about the mass. If it will be a positive, meaning that the force is downwards, positive mass, or negative mass. Negative mass again means that the force is going upwards, and since we have this third button on the balance, if we set this third button to 0 when there is no current, means that if we are having the force going upwards, means that we will have a negative mass, and if we have positive mass, means that the force is downwards. Okay, that's the way we measure positive or negative force, by measuring positive or negative mass, upwards or downwards on the balance, right? And here you have the constants, which are the permittivity of the free space, number of turns, which is identical on both coils, the length of the coil, which is the exposed section of the coils, which is the wire, basically, two wires identical, distance between the two wires, and the constant G. Okay? And that's it. Good luck.